In this lab, we observed the motion of a spring system as it oscillated in a swinging motion. The purpose of this lab was to demonstrate the interactions between kinetic and potential energy within a system, using the energy principle as a fundamental principle that describes the nature of the motion. A computational model of the mass's motion was then made using VPython. Within this computational model, I used the energy principle to write code that graphically visualized the values of kinetic, potential, and total energies. As a result, I found that the total energy change remained zero, which indicated that the energy was neither entering nor leaving the system and total energy remained constant. I first began analyzing the video using Tracker. In order to do so, I set my origin at the top of the spring as shown here. As you can see, in the beginning of the clip, the object is hanging motionless. The length of the spring at this instant in time is 0.7 meters. The fact that there is no movement tells us that the net force is zero. Because the net force is zero, we can assume that the two forces acting on the mass, the spring force and the weight force, are equal at this point in time. In order to create a computational model for this motion, we must first find the spring constant k. The following equation, t squared equals 4 pi squared times m over k, relates the spring constant k to the period length. Thanks to Tracker, we can determine the period length and use that value to solve for the spring constant. To do so, I found the average time span between each peak in Tracker's graph of the ball's position. This value came out to be approximately 1.52 seconds. By plugging this value into the previously shown equation, I found the spring constant to be approximately 6.87 newtons per meter. Now I am able to begin creating a code to model the observed motion. For the initial position of the ball, I found the corresponding x and y values of the ball at time t equals 0 in Tracker. This is the program that will model the ball's motion. As you can see, there are essential components such as the ball's mass and the initial positions written in code here. In order to write code to represent the net force acting on the ball, I had to first be aware of all the forces acting on the object throughout this example. In this case, only weight and spring force act on the mass. Weight is represented by the line negative ball dot m times g times j hat, as has been the case for several previous labs. The spring force is represented by the line negative k underscore s times L hat, where k underscore s is the spring constant that I calculated. S is the difference between spring length and relaxed length, and L hat is a unit vector indicating the direction of the spring. Once the essential parts of the code were established, I was able to gain further insight into the behavior of the system by analyzing the potential, kinetic, and total energy of the system. For this observation, according to the energy principle, total change in energy is equal to the sum of the change in gravitational potential energy, kinetic energy, and spring potential energy, as shown by the following equation. Kinetic energy is equal to 1/2 times the mass of the object times the square of the velocity. Change in kinetic energy is simply the difference between the final kinetic energy and the initial kinetic energy. The magnitude of gravitational potential energy is equal to the weight force times the magnitude of the y position component, and therefore it can be represented by the code ball.m times g times ball.position times y. The value for spring potential energy is equal to 1/2 times the spring constant times s squared, where again s represents the difference in length between resting position and observed length L. Lastly, I imported Tracker's data of the observed motion into this code so that the computational model and the observed motion could be easily compared. Here's the program in action with the modeled motion, along with corresponding graphs of total energy, kinetic energy, and potential energies. From the graphs, we can see that the change in gravitational potential, kinetic, and spring potential energies all oscillate, but the total energy change remains zero throughout. This is because we chose the Earth, the spring, and the mass as our system. This being said, there is no energy transfer in or out of the system. so total energy remains constant and energy change is zero. This statement agrees with the fundamental principle, the energy principle, because total change in energy is equivalent to the sum of the changes in potential and kinetic energies. If the total system energy change is zero, then the sum of the kinetic and potential energies must also be equal to zero. Therefore, the energy principle is in fact satisfied. Also note that it does not matter whether you use the x or the y components to determine the period length. The period length will come out the same regardless.